Picture this. It's 2022, and you're watching an AI generate a breathtaking Renaissance painting. Every brushstroke perfect, every shadow precisely rendered. Light dances across water with photorealistic beauty. Then you ask it to create a simple coffee shop sign that says coffee, and it produces illegible alien cuneiform. How is it that artificial intelligence could master the complex interplay of light and shadow, yet completely fail at spelling a five-letter word?
Welcome to Mindcast. I'm Will, and today we're diving into one of the most fascinating paradoxes in modern AI development. What you just heard isn't science fiction. It was the reality of generative AI just 2 years ago. Today, I'm breaking down a groundbreaking technical report called The Architecture of Legibility, a deep dive into how researchers solved what seemed like an impossible problem.
Here's what we're going to uncover. Why AI could paint like Picasso but couldn't spell like a kindergartner. The hidden bottleneck that was sabotaging every text generation attempt, and 3 revolutionary approaches that changed everything, from Google's brute force scaling to a startup's surgical precision, to a completely new way of thinking about AI architecture. By the end of this episode, you'll understand not just what happened, but why it matters for the future of how we interact with artificial intelligence.
Let's start with the paradox itself, what researchers call the typographic paradox. Early generative models like Stable Diffusion and DALL-E were genuinely miraculous in many ways. They could understand and render incredibly complex visual concepts. Ask them for a steampunk elephant in a Victorian library, and they'd produce something that would make concept artists weep with envy.
But ask for a simple neon sign reading open, something any sign maker could create in minutes, and you'd get garbled nonsense. Letters would be missing strokes, words would be scrambled, and the spacing would be completely wrong. It wasn't that the AI didn't understand the concept of text. It clearly knew what a sign was supposed to look like. It just couldn't execute the fundamental act of visual spelling. Think about how strange this is from a human perspective. For us, recognizing complex scenes and writing simple words use completely different cognitive processes. But these AI systems seem to have it backwards. They excelled at the complex and failed at the simple. This paradox haunted the AI community for years because it revealed a fundamental misunderstanding about how these systems actually work. The breakthrough came when researchers realized they weren't looking at the right place. The problem wasn't in the image generation itself. It was buried much deeper in a seemingly mundane process called tokenization. And here's where the story gets really interesting, because the solution would require rethinking some of the most fundamental assumptions in AI development.
So, what exactly was going wrong? The culprit was something called character blindness, and to understand it, we need to take a quick detour into how AI systems actually process language. When you type words into an AI system, it doesn't see letters the way you do. Instead, it breaks your text into chunks called tokens through a process called tokenization. Now, the most common approach was something called byte pair encoding, or BPE. This system was actually brilliant for language processing. It would compress common word fragments into single tokens. So coffee might become one token, or maybe cough and fee. This compression made language models incredibly efficient at handling vast amounts of text. But here's the fatal flaw. When you ask these systems to generate an image of a neon sign saying coffee, the text encoder would pass along just one unified token representing the whole word. The image generation system never actually saw the letters COFFEE. It only saw an abstract representation of coffeeness. It was like asking someone to write a word in a language they'd never seen the alphabet for. They might understand the concept, but they couldn't form the individual letters.
This is what researchers called character blindness. The AI was literally blind to the individual characters that make up words.
It had learned to associate the token coffee with the general visual pattern of that word, the overall shape, the relative proportions, but it had no understanding of the sequential rules of spelling, no grasp of how letters combine to form meaning. The implications were devastating. If a word didn't appear frequently in training data, the system couldn't render it accurately. Rare names, technical terms, creative spellings, anything outside its memorized visual patterns would come out as gibberish. It wasn't generating text, it was hallucinating approximate visual textures that vaguely resembled text. Once researchers understood the problem, 3 major approaches emerged to solve it. Each represents a fundamentally different philosophy about how to build AI systems, and together they tell us something profound about the future of artificial intelligence. Let me walk you through each one. First, there was Google's approach with their image gen model, brute force scaling. Google's team made a counterintuitive discovery. Instead of scaling up the image generation model, which is what everyone expected would improve quality, they found that scaling up the language understanding component had far greater impact. They replaced the standard text encoder with a massive language model called T5XXL, 4.6 billion parameters of pure language understanding power. This model had been trained on billions of documents and possessed an incredibly deep grasp of language semantics and syntax. When it processed text prompts, it could maintain much richer, more detailed representations of what words actually meant and how they should appear. The results were dramatic. Imagen could suddenly handle complex typographic prompts, text rendered out of unconventional materials, creative layouts, even abstract concepts like sprouts in the shape of text coming out of a book. Google had essentially overwhelmed the character blindness problem with raw linguistic intelligence. The second approach came from a startup called Ideogram, founded by former Google researchers. Where Google used brute force, Ideogram used surgical precision. They designed their entire model around text rendering as the primary objective, not a secondary feature. Ideogram's breakthrough was architectural. They created what they called a tripartite text embedding system. Instead of relying on one encoder, they used 3 specialized components: dual clip models for visual language relationships, a T5 encoder for linguistic syntax, and here's the killer feature: a custom typography layer. This typographical layer was trained specifically on the relationship between characters and their visual glyphs. It understood kerning, the spacing between letters. It grasped how lighting interacts with 3D text. It could validate that generated visual patterns precisely matched the requested linguistic symbols before finalizing the image. The results speak for themselves. Ideogram achieved 90 to 95% text accuracy, while competitors like Midjourney were still struggling with 30 to 40% accuracy rates. But the third approach? This is where things get really revolutionary. Google's Gemini 2.0 Flash represents a complete paradigm shift: native multimodal generation. Instead of having separate systems for understanding text and generating images, Gemini processes text, images, and audio all within the same unified neural network. This eliminates the translation problem entirely. There's no awkward handoff between a text encoder and an image generator, because the semantic concept of a word and its visual representation exist in the same cognitive space. It's like the difference between having a translator relay instructions versus understanding the instructions directly in your native language. What's fascinating is that Gemini uses something called block parallel denoising. Instead of generating images pixel by pixel like traditional methods, it refines entire blocks of visual information simultaneously. This approach leverages the reasoning capabilities of large language models while maintaining the spatial precision needed for accurate text rendering. Now, there's a fourth angle to this story that's equally important: the data revolution.
OpenAI's approach with DALL-E 3 revealed that architectural improvements alone weren't enough. The problem also lay in the training data itself. Traditional datasets relied on basic alt text scraped from the internet. An image of a bustling street with a neon sign reading "Open 24 hours" might be labeled simply as "a store at night." The visual information was there, but the semantic connection to the specific text was completely missing. OpenAI's solution was synthetic recaptioning. They built an advanced AI captioning system that could perceive and describe every detail in an image, including the exact spelling, location, and style of any text present. When they retrained their models on these incredibly detailed synthetic captions, the AI finally had the data it needed to understand the relationship between textual concepts and their visual representation. So what can we learn from this journey from gibberish to mastery? I want to share 3 key insights that extend far beyond just AI text rendering. These are lessons about how we approach complex problems in any domain. First, the bottleneck is rarely where you think it is. For years, researchers assumed the problem was in the image generation pipeline. They tweaked models, adjusted parameters, tried different architectures. But the real issue was hidden in the seemingly mundane tokenization process, the very first step of converting text to numbers. This reminds us that in any complex system, the constraint that limits performance might be buried in an unexpected place. The key is to trace problems back to their absolute foundations. Second, there's never just one path to breakthrough. We saw 3 completely different approaches succeed: Google's computational brute force, Ideogram's architectural precision, and Gemini's unified reimagining. Each worked because it addressed the core problem from a different angle. This suggests that when facing seemingly intractable challenges, we should explore multiple solution vectors simultaneously, rather than betting everything on a single approach. Third, and perhaps most importantly, the quality of your input fundamentally limits the quality of your output. OpenAI's data recaptioning breakthrough reminds us that even the most sophisticated AI systems are constrained by the information they're trained on. In any domain, whether you're building AI systems, training teams, or making strategic decisions, the quality of your foundational data and assumptions will ultimately determine your success. But here's what excites me most about this story. We're witnessing the emergence of a new generation of AI that doesn't just process information, it truly understands the relationships between different modalities. Text, images, audio, and video aren't separate domains anymore. They're different expressions of the same underlying intelligence. This shift has profound implications. We're moving toward AI systems that can engage in real-time conversational editing of visual content. Imagine asking an AI to make that logo bigger, change the font to something more modern, and fix the typo in the 3rd line, and having it understand and execute those changes instantly, maintaining the context and style of the entire design. The frontier now isn't basic text rendering, it's enterprise-grade document synthesis, creating complete infographics, multi-slide presentations, dense technical reports with perfect typography and layout. The same architectural principles that solved the coffee shop sign problem are scaling up to handle entire visual documents. And here's the kicker. This extends into video. Models like Google's Veo 3 are now maintaining text consistency across hundreds of frames, handling dynamic lighting changes and camera movements while keeping every letter crisp and readable. We've gone from alien cuneiform to cinematic sequences with embedded text in just 2 years. The journey from visual gibberish to typographic mastery reveals something profound about the nature of intelligence itself, both artificial and human. The ability to seamlessly translate between abstract concepts and concrete representations, to understand not just meaning but also form, to maintain consistency across different modalities. These are hallmarks of genuine understanding.
Today's AI systems have crossed the typographic threshold. Accurate, stylized, multilingual text rendering is no longer remarkable. It's the baseline expectation. We've established a new technological standard where the seamless integration of text and visuals is simply how AI systems work.
This has been Mindcast. I'm Will. If this deep dive into the hidden mechanics of AI breakthrough fascinated you as much as it did me, subscribe wherever you get your podcasts. Next week, we're exploring another AI mystery: how systems learned to understand and generate music, and why rhythm turned out to be the hardest part. Until then, keep questioning, keep learning, and remember, the most important breakthroughs often come from examining the parts of the system that everyone else takes for granted.